Hey everybody, welcome back. I'm sorry I can't be there with you, and I know this is not an ideal format for light demonstrations. Hopefully everything comes through okay in the video. We'll only have another option, so we'll just run with it. So here's the stuff that I wanted to show you with light that we didn't get to before I left, and then you'll have an activity later on today where you'll be a little more active and moving. So my apologies if I'm a little long-winded here. Let's get right to it. When light hits something, there's three things that it can do. We've got reflection, absorption, and transmission. So let's go through each of those. Reflection we talked a little bit about. That's where light bounces off of something, and something special happens there with angles. Whatever angle the light hits at, it also leaves that surface at. So if we call this the angle of incidence and this the angle of reflection, you can write an equation that this angle is equal to this one. We don't have to worry about the math of it. We just have to recognize that if we hit at this angle, we're going to bounce off at this one. If we hit at this angle, we're going to bounce off like that. If we go straight in the mirror, we're going to bounce straight away. So whatever that incoming angle is, we'll always have the same outgoing angle. That's called the law of reflection. You don't need to know the name, but when you take a physics class later on, you'll say, oh yeah, I remember the law of reflection. Incoming, outgoing angles are the same. And one more representation of that, if these are our rays of light, we have to have this flat mirror for that to work well. It turns out that that law always holds true, but if we have a rough surface, we're not going to get a nice regular reflection like this. We're going to get something a little bit more chaotic, and that'll show up in just a minute. We have two different types of reflection. So the regular reflection is where all the rays of light that come in together leave together as well. With diffuse reflection, we have a rough surface that's doing the reflecting. So they all come in together, but they're all going to hit a little different parts of the bumpy surface. So they'll end up kind of scattering afterward. We saw this last week, which actually is today for me, because I'm recording this Friday afternoon. We saw it when the laser light hit the ceiling and then it illuminated the whole room. Right now, in fact, you're seeing this on my face. There's a light from the projector hitting my face, but when it leaves my face, it just looks like my face. You don't see see the light moving all in one direction. There's not a beam of light shooting out across the room here as I shift my face around. So it's just lighting up my face. It's reflecting off of my face and getting to the camera, getting to your eyes. So specular or regular reflection, when we think about seeing a reflection, that's typically what we mean. We mean that we see a nice clear picture of the thing. So here's a good example of specular or regular reflection. We have this nice smooth surface of the water, so light from the mountain is leaving the mountain, it comes down and hits the water, it bounces up and it gets to our eyes, or it gets to the camera in this case. That happens whenever we have a mirror smooth finish on the surface. Diffuse reflection, we don't have that same mirror smooth surface. So we have a bumpy surface, and so even though all those rays will bounce off that surface at whatever angle they hit at, the angle is different because the surface is so rough. So we end up with rays of light going all over the place, like we have here. See light going out in all different directions when it's hitting, looks like maybe a sheet of paper here with the laser line. So we don't see another beam of light coming off in this direction like we would with a mirror. When we see things, what must be happening there is either that thing has to be lighting up itself, or something has to be lighting up nearby, and then the light from that light source hits that surface and bounces off in all different directions. And so when you're seeing me right now in the video, I'm being illuminated by the projector, and then that light, after it hits my face, it goes off in all different directions. So if anyone else were in the classroom with me, instead of me just talking to an empty room like a weirdo, everybody in the classroom, all around the room, would be able to see my face because the light is bouncing off in all different directions. Another thing that can happen when light hits a surface is absorption. So if you've been outside on a hot day wearing a black t-shirt, you've felt absorption going on. If you did the solar oven project, your whole project was about absorption. So the light comes in, it hits the atoms, and instead of bouncing off the atoms, it gets absorbed by them, which means that the light actually disappears, and instead of having light energy, we have thermal energy. The atoms shake a little bit more as a result of that collision. So any light that gets absorbed doesn't get reflected, or the other thing is transmission, doesn't get passed through the material. So that energy is lost as light. It's changed into a different form. So we know that some colors absorb more light. Black is black because, well, black is how we describe this sensation of seeing something where very little light is coming off that surface. So this black dog out in the sun, he's getting really warm and he looks black to us because very little of that light makes it off of his fur and back to our eyes. Instead, most of it is getting absorbed by the atoms in his body, which means they start to shake, which means he feels hot. Poor puppy, get him some water. All right, back to this thing about vision. You only see the light in the visible part of the spectrum that gets to your eye. And that's either from an object that's emitting its own light or an object that is having light bouncing off of that surface. That's just repeating what we've already seen. Now, color is an interesting topic. We have the whole spectrum of color. We also talked at the very beginning of this unit about how our brains can be fooled with colors. We have parts of our eyes that are sensitive to these different colors, and then our brains have to interpret signals from those parts of our eyes. And so we have places where confusion can come into play. One thing that we have to deal with is what if we get signals from more than one of those cells? We have to interpret that somehow. Sometimes we'll have multiple colors of light all together. They mix together, and we interpret that as a new color, some color that isn't actually there, that our brain invents. White light is just a mixture of lots of different colors of light. Black is the absence of light, or very, very little light coming from something. So our eyes have two different types of cells, two broad categories, rods and cones. The rods are for seeing in low light, so when you turn out the lights and you're trying to walk around in the dark, eventually you start being able to see a little bit better in the dark. Those are the rods becoming active. They're only active in low light conditions. They don't see color, so everything will lose its vividness in the dark. You may not even be able to tell what color something is. Cones are able to see color. We have three different types that see three different ranges of colors, and that's how we're able to distinguish one color from another. This cone cell sees it, but this one doesn't. Okay, that must mean it goes with the cone cells that this other one can see. We have three types that have some overlapping sensitivities to color. So we call them red, green, and blue cone cells. R, G, and B is the acronym there. Most computer displays work in, or phone displays or TV displays, they work in RGB, and they mix different amounts of red, green, and blue because that's what our eyes are sensitive to anyway. So when we see something that is yellow, what happens, there's actually yellow light, that is a real thing. But what happens when we see yellow light is the green cells say, hey, I'm active, I see some light here. And the red cells say, hey, I'm active, I see some light here. And your brain gets a signal and says, all right, red and green are both seeing this light, so let's interpret that, and we interpret that as this color, yellow. The blue cells, meanwhile, they don't see anything from that. And they don't interpret that as anything. So there's no signal from the blue cells. Now, we can fool the eye into thinking colors are not there by mixing different colors, different amounts of red and green light, to make it think that it's getting the same signal it should when it gets something like yellow. Color blindness is about missing one of those three sets of cones. So, for example, if you were missing, say, your red cells here, then these colors over here are going to be tough to tell apart from one another. So if you only have blue and green cones in your eyes, then yellows and reds will all, and greens even, will all kind of look about the same to you. Because right now, with three sets of cells, if I have a color over here, I get a strong signal from green and a weak one from red. But if I get a signal over here, I get a weak signal from green and a strong one from red. If I get rid of the red ones, though, all I see is just strong or weak signals from green. So it's just some color in brighter or darker instead of different tones. So color blindness, we don't really have a way to say this is what it looks like to somebody who's colorblind. But what we can say is that there are three different types of colorblind, actually a few more, but the common ones are just missing one set of cells. So if you have protanopia, you're missing the red cone cells in your eyes. And we know that people with protanopia, they can't tell the difference between these two pictures. So this picture and this picture would look the same to them. I can't say that this is what it looks like, me as a normal vision person. I can't say that this is what it looks like to have protanopia. But I can say that if you show somebody with protanopia these two pictures, these two will look the same or very, very close to each other anyway. So notice that we're losing a lot of detail and being able to distinguish these colors up at the top. So this is that one that we just looked at. We're missing the red cells, then the reds, the oranges, the yellows, the greens. They all look pretty similar to each other. Deuteranopia here, we're missing the green cells. Tritanopia, we're missing the blue chrome cells. And so we see different areas that are easier to distinguish and areas that are tougher to distinguish with color blindness. This is that artifact of how our brain gets tricked into thinking there are colors there that aren't really there. So this actually isn't yellow. You're not seeing yellow right now because the projector that's sending this out doesn't have a way to make yellow light. It can only make red, green, and blue, but luckily that's enough to fool your eyes most of the time. So let me show you something with that. I've got this little device here that lets me shine red, blue, and green light up on the screen. And we'll see how well this shows up in the video. Hopefully we'll get something here. Okay, yeah, that looks pretty good. So this has just been sitting at the front of the room. Maybe you've seen it already. This is just 3 flashlights in a little stand. So we've got one that can project blue light, so we can shift that around a little bit. One that does green light and one that does red light, all separate from each other. And if I mix 2 of these together, I'll start seeing colors that aren't really there. So we talked about red and green. When we mix those 2 together, we see yellow light there. There is no yellow there, but our eyes interpret it that way. Because when we see something that's actually yellow, red cells and green cells both get activated. If I see red and green light in the same place, red cells and green cells both get activated. And so it's the same signal going to your brain. So we see yellow when red and green mix. When green and blue mix, we see a color we call cyan, so light blue there. And when we see blue and red mix, we get maroon. And then when all 3 mix, we end up with white. And so white is the presence of all these different cells activated at the same time in different amounts. Now, if I try and illuminate something with these different colors, I get some interesting effects from that sometimes. So let's see if I can get this set up where I don't have to hold it. That should do the trick. Okay. So I have these little cards here. And they have writing on them in different colors. And it'd be a little tough to see from the picture maybe. We'll see how this works. I may be talking to nobody because this might get cut out. We'll just have to wait and see. So I have this one that has the word blue written on it. Oh, I sure hope you can see some of this. Now, if I put that into the blue light, I can still make out the word blue. So when I wrote the word blue here, I wrote it just with blue ink. It's printed out in blue ink, which means that it's really good at reflecting blue light. It's not very good at reflecting red or reflecting green. Those colors mostly get absorbed. So if I put this into red light, I can't see those letters anymore. That's just pitch black. Or green light, I can't see those letters anymore. It's just pitch black. So I end up with just no light coming off of this surface anymore. Because here, red light works especially well with this. The red light is not reflected by those letters. Now if I put it into an area where it's mixing, that red light gets absorbed still, but there's blue light here too, in the maroon section. And so the blue light gets reflected, the red light gets absorbed, and I'm still able to see the blue light. Try another one here, like magenta. So this zone right here is magenta. If I put that in the white light, I can make out the letters. It's in a magenta color. If I put it in the magenta colored light, it still looks the same color to me. Magenta things are really good at reflecting red light and reflecting blue light, but they don't really reflect green light. So if I put it over here in the green, I don't really see much of anything. It's mostly black, a little bit gray maybe. If I put it down here in the red, then it looks red to me. It reflects the red light that's present. If there were blue light, it would reflect that too, but there's only red light here. If I put it in the blue, it reflects that too. If there were red light, it would reflect that as well, but there's not. There's only blue light here, so I see blue. If I do it here, I see still blue light. So the blue light gets reflected, the green light gets absorbed. Here I can see a nice contrast between those two. So this area right here is black, or very close to it anyway. And here I'm still seeing blue from that, so I see the blue light from this circle gets reflected. The green light from this circle does not. So where I have both of those, I still get that blue light reflected. Where it's only green, it gets absorbed. You can play around with colors and get some interesting effects as far as what color things appear under different lights. You saw, that's not what I wanted. You saw an example of that last year, the year before, with what color is the dress meme that was so popular for a while. The idea is that things look different colors under different colors of light. Your brain filters out some of that lighting information, but sometimes it does a better job than other times. So when people saw different colors there, some people were filtering out that lighting information in a different way than others were. All right, so mixing light, I talked through all this already, so I'm just going to skip over that. This is a zoomed in view of a cell phone screen, so you can see that there are no yellow pixels or magenta pixels or cyan pixels or pink pixels. There's only red, green, and blue. But if you mix those colors in different amounts, you can make all the other colors. So you can still see all the colors. It's not just limited to those three on your phone, even though your phone doesn't actually put out any light other than those three colors. This is the same thing that we were just looking at, just maybe an easier to see form. So red, green, and blue. And I think it's worth writing down in your notes, maybe for an assessment tomorrow, this little diagram. So a Venn diagram with the three circles. And we've got some overlapping parts here. So red here, where that overlaps with blue, this color is magenta. Blue here, where it overlaps with green, is cyan, C-Y-A-N, that's up here too. Where green and red overlap, we've got yellow. And where all three of them overlap, we've got white. So anytime you mix red, green, and blue together in equal amounts, you get those three other colors. We call red, green, and blue the primary colors for light. Cyan, yellow, and magenta would be the secondary colors for light. And yeah, I know it doesn't work that way with paint. That's mixing pigments instead of mixing light. And we did that with the examples, but just in case it didn't come through, just a real quick run through on this. Red things like an apple are good at reflecting red light. Not good at reflecting green and blue. They absorb green and blue light. So if we put a red light on a red apple, that red light gets reflected. If we put a green light on a red apple, the green light gets absorbed, and so we don't see any light bouncing off the apple. When something doesn't have any light bouncing off, then it looks black to us. So a red apple under green light would look black. A red apple under blue light would look black. A red apple under yellow light, or a mixture of green and red light, the red reflects, so we see the red. The green absorbs, so we don't see it. And so we only get the red light. Here, the red apple still looks red. All we care about for vision is the light that gets to our eye. So the light that gets absorbed in the apple or the banana or whatever else, that doesn't get to our eye. We can't see it anymore. So if you ask the apple what color it is, it might say, well, nothing, apples don't talk. But if it could, it might say, well, gosh, I keep all the green light and the blue light that hits me. I guess that makes me cyan, combination of green light and blue light. But what we're interested in is all the light that leaves the apple, not the light that stays with the apple. The light that leaves the apple is the red light. Yellow bananas are good at reflecting both red and green light, not very good at reflecting blue light. They mostly absorb blue light. So if you put a yellow banana under blue light, it would absorb that light and it would look black. If we put it under magenta, so it'd be red and blue hitting that banana, Under magenta light, the yellow banana would look red because the red light gets reflected, the blue light gets absorbed, so all we see is the red reflected light. There's no green light to worry about, so not to think about that. White light is a mixture of all the colors, so whatever gets reflected, we'll see. Whatever gets absorbed, we will not see. We don't have to think about any special cases of light. Subtractive color is what we call it when we mix pigments. You don't need to do anything with this for the assessment. This is probably closer to the color wheel you're more familiar with, but I think you probably learn red, yellow, and blue instead of magenta, yellow, and cyan. Blue would be one of the primary colors, but notice here it's actually a secondary color. Red is also a secondary color in this one. Printers all use red, magenta, yellow, and cyan color pigment to make all the other colors. So it turns out to be a little bit better set of colors to use as the primary colors than the yellow and blue. But you can still make lots of colors with red, yellow, and blue, so that's a perfectly acceptable set of primary colors. I'm going to skip over the phosphors. The three things it can have in the light when it hits something: it can get reflected, it can get absorbed, and the last one is it can get transmitted. It can pass right through that new material. If we have something like a light wave going into glass, we'll also notice that that light wave will kind of get bent as it transmits into the new material. So we get something called refraction happening there. So the angle that it's moving through changes. We're not going to do anything with calculations of angles or really much of anything with refraction, just for completeness sake. That's the last thing that happens when light hits a boundary. So to summarize, reflection, the light hits that surface and bounces off. Sometimes it bounces off altogether, sometimes it scatters when it bounces off. If we've got a nice smooth surface, the light reflects altogether. If it's a bumpy surface, then the light scatters when it hits it. And we are talking really, really smooth, so like a mirror smooth finish for it all to reflect together. Absorption, that light just goes away. It doesn't exist as light anymore. That energy has turned into thermal energy, runs into the atoms and makes them shake, and the light disappears. The energy is thermal energy of the shaky atoms instead. And with transmission, that light can actually go right through the material. So the light that's hitting me right now, it goes through the air to get through me, so it's transmitting through the air. If I shine a flashlight into a fish tank, the light goes right through the water. So there's transmission going on there. Oftentimes we'll have some amount of each of these, a little reflection, a little absorption, and a little transmission, or maybe a lot of one and just a little of the others. But that's it. That is the last of what we have to know for the light material, and the last of what we have to do for the assessment. So the rest of today, you get to play around a little bit with the reflection part of this. You can't really do the math yet for refraction, but the math you can do intuitively without calling it math. You can do that for reflection. So the rest of the period is going to be playing on that. Let's introduce that next.